In problem number 2, the question is, if the driver in this problem took 21, the delta time interval here is 21.1 minutes, and here this trip took delta time 2 is 7.5 minutes. What was the average speed? What was the average speed? And finally, what was the average velocity? Okay, the average speed, I'm going to put that over here. Oops. This delta T2 was 7.5 minutes. The average speed is the total distance traveled divided by the total time. So again, the total distance traveled is 48.6 kilometers divided by the total time, that's delta time 1 plus delta time 2. Okay, and this gives 48.6 kilometers divided by 28.6 minutes, or that's 1.70 kilometers per minute, and that's a velocity, kilometers per minute. Okay, that would be the average speed. That's part A. Part B is the average velocity. Again, the velocity is defined as the displacement divided by time. The final displacement is only 22.2 kilometers divided by the total time, which again is 28.6 minutes. So the final velocity is 0.776 kilometers per minute, traveling in the plus x direction. There's the speed, and there's the magnitude, and there's the direction. So notice that the difference between speed is the average speed was the total distance over the time. The velocity is going from the initial position to the final position divided by the time. Okay. That's problems 1 and 2. Okay, let's go over problem 3. A plane flies straight for 672 kilometers and then turns around and heads back. The plane then lands at an airport that is only 321.9 kilometers away from where the pilot turned around. He gives the average velocity over the entire trip. How much time did the trip take? So we first have to plot the actual plot. Make a picture when you do this. Here's your x-axis. The plane flies straight for 672.1 kilometers. At that point, he turns around and he lands at an airport that is only 300, this distance from here to here. He lands right here, this distance here. is 321.9 kilometers. Okay? And he's saying, they say that the average velocity, which we know was the final displacement over the time, is 42 meters per second. Okay? So, we know that this delta x here, this displacement, goes from here to here. This is delta x, the final, this displacement from the initial to the final. So, we have to know what this is. This is going to be this total distance minus this. So it'll be 672.1 kilometers minus 321.9. Okay. 672.1 minus 321.9, and we get 350.2 kilometers. So this displacement is 350.2 kilometers in the plus x direction. So the question is to solve for the time. So if we take this equation here, we know what that is. We know what this, we don't know what this is. So we solve for time, and we say delta x equals 42 meters per second times delta t. We divide by this quantity, we get delta x over 42 meters per second equals delta t. So delta t is equal to 350.2 kilometers over 42 meters per second. Now notice, we do have a units problem here. The numerator here is in kilometers, the denominator is in meters. So let's convert from kilometers to meters here. Let's see, can you all see this? I'm going to shift this up here. Delta t is 350.2 kilometers divided by 42 meters per second. We know that 1 kilometer is equal to 1,000 meters. Notice the kilometers cancel out. And notice also that this meter will cancel out with this meter, which is giving us units of 1 over seconds, which is the same thing as seconds. So we will have the answer. The final answer then would be 350.2 times 1,000 divided by 42, or 8,338 seconds. And if we divide that by 60, that's 130, we'll call it 9 hours. Excuse me, minutes. If we divide it by another 60, that's 2.3 hours. Notice here, because from a significant figure point of view, this has 4 significant figures, but this quantity here only has 2 significant figures. And so really we should limit our final answer to 2 significant figures. So this would be, if we wanted to leave it in seconds, we could certainly say 8,300 seconds. Or to make it clear, if we wanted to make it clear that only the 8 and the 3 were significant, we would say 8.3 times 10 to the third seconds. This makes it clear that only the significant figures are 8 and 3. So hopefully that's clear. Okay. Okay. Let's do number 4. Let's do number 4. And then after number 4, we will jump around a little bit and not necessarily, instead of doing the questions, I will give you an idea of how to do the questions for all the rest of the questions. But let's go ahead and do number 4. An athlete runs 1,600 meters down the straight road. On the first 800 meters, the runner's average velocity, so let's do this. Let's draw an x-axis, always draw a picture. He starts at x equals 0, and he runs a total of 1,600 meters right down the road. The first 800 meters, the average velocity during this portion of the time, the average velocity is 6.50 meters per second. Over the remaining, from 800 meters, from here to here, the average velocity went down. I'm going to say average velocity. The average velocity is only 4.30 meters per second. Okay. Now the question is, what is the average velocity over the entire stretch? Okay. What's the average velocity over the entire stretch? Now, there's a little bit of trick. We can say what we want is the average velocity from here, from the start to finish. Many people will look and say, oh, well, we simply take this number, take that number, we take the average of the two, we add them up and divide by 2. They would say, well, the average velocity is 6.50 plus 4.30 meters per second, add them up, and simply divide by 2. Is that right or wrong? That's wrong. That's not the right answer. Now, why isn't this the right answer? It's not the right answer because the length of time, this interval here, is not the same as the second time interval. How do we know that? We know that because they travel the same distance, 800 meters, but their velocities are different, so therefore the time spent in the first interval is different from the time spent in the second interval. So we can't average velocities if the time intervals are not the same. So if we what we actually are forced to do in this case is we actually, in order to calculate this correctly, now remember, the average velocity over the entire trip, the average velocity, is the total displacement, which we know is 1,600. We know what the final displacement is. It is 1,600 meters, divided by the total time. The problem is we don't know what the total time is. And so what we really need to do is to find out what the total time is. So we really have to, first of all, figure out, break it up into 2 parts. We have to figure out T1, then we have to figure out T2, then we add them together. So remember, velocity is equal to distance, the displacement over time. So we'll call it V1 is the displacement 1 over T1. So that means that solving for delta T1 is the displacement 1 divided by the velocity 1. So this would be displacement number 1 is 800 kilometers divided by 6.50 meters per second. Excuse me, that's not kilometers, it's meters, 800 meters. 800 divided by 6.5, and then we get 123 seconds. That's for, and we round it off to 3 significant figures. Divided by 6.5. That's right. So T1 is 123 seconds. T2, I'm going to do that up here, likewise is delta x2 divided by v2. Again, 800 meters, but the velocity is different, divided by 4.30 meters per second. This would be 800 divided by 4.3, 186 seconds. So the total sum of these, 123, the sum of these, the total time, can you all see down here? I hope so. The total time is 309 seconds. So this total time from start to finish is 309 seconds. Once we have the total time, now we can find truly the correct average velocity. The average velocity is 1,600 meters divided by 309 seconds. 1,600 divided by 309 seconds is 5.18 meters per second, and he's traveling in the plus x direction for his direction. So that would be how you would do problem number 4. Okay, now for the rest of the problems, what we're going to do is I'm just going to give you an indication of how you do the problems, but we won't actually work them out. Hope that's okay. Problems 5 and 6 refer to this figure that's on page 35. And it's a plot of time on the x-axis versus position, which is x in the y. And it starts at 0, is plus x and minus x. And it looks something like this. It crosses the x-axis, and then it comes down here like that. So, number 5. The question says, at approximately what time does the car change its direction? Okay? At what point does the car change its direction? Well, the car, remember, we're plotting position versus time. Now, what is the slope? The slope of this is the change in position over change in time, which is velocity. So the slope of this curve is the velocity. So imagine that this is the x dimension, and here's 0. And this represents, the marker represents the car. The car starts off going in the x direction, and notice He starts off at a certain speed, and notice the speed picks up. The slope goes up, so it goes real fast, and then at this point, the slope becomes 0. So what happens? He actually stops his velocity. Now he starts his negative velocity. So what does that mean? Negative slope. The velocity is going the other way. It's going the other way, going the other way. He crosses the x position, and it keeps on going in a negative direction. So the question is, approximately what time does the car change its direction? It changes direction right at the peak, right where the slope goes from plus to negative to 0. So he's going this direction, and then he changes direction. Okay. Number 6, over what time interval is the car moving the fastest? The car is moving the fastest whenever you have the steepest slope. Wherever the steepest slope is, that's where the car is moving the fastest. It might be going in the plus direction, or it might be going in the negative direction, in the minus direction. Okay. And question number 7 is, question number 7 doesn't have anything to do with this graph. Okay. Maybe we should go over that. Okay, question number 7. A train is traveling with an initial velocity of 20.1 meters per second. If the brakes can be applied with an acceleration, it gives you what that acceleration of minus 0.0500 meters per second squared. How long will it take for the train to stop? Oh, that's a very good question. Okay, so what that means is, think of it this way. We have an initial velocity, and it is 20, I'm going to write this bigger. We have an initial velocity of 20.1 meters per second. Okay. At some point, let's say t equals 0, the train's traveling at a certain velocity, and right at this point, he starts to apply the brakes. He starts to deaccelerate. He applies the brakes such that the acceleration is negative 0.0500 meters per second squared. Is that right? That's right. The question is, how long will it take to stop? At some point, now, when will he stop? He will stop whenever the final velocity is equal to 0. That's when he stops, right? It makes sense. So, what is the definition? Now, how do we solve this? The question is, how long will it take to stop? How long will it take to go from this initial velocity down to where the velocity is 0? We can solve this by using the definition of acceleration. Acceleration is equal to the change in velocity over delta t. Okay? Now, what we're solving for is delta t. That's what we're solving for. What's the definition of the initial, or the delta v? It's the final velocity minus the initial velocity over delta t. Okay? So, we know what the acceleration is. We know what the final velocity is. We know what the initial velocity is, but what we don't know is what delta t is. So let's solve for I always like to solve for what the unknown variable is first using algebra. I would encourage you to do the same thing. Let's do that. Delta t is equal to the final velocity minus the initial velocity, all divided by the acceleration. Now, the signs here are very important. We have to keep the signs straight. Otherwise, we'll get the wrong answer. the final velocity is 0. Okay? Minus, what's the initial velocity is 20.1 meters per second. Okay, 20 minus 20.1. Notice that's going to be a negative number, but that's okay. What's the acceleration? The acceleration is a negative number too. So we put the acceleration in, minus 0.0500. Notice 3 significant figures, meters per second squared. And I'm going to write it up here so you can see it. So that means delta t is 20.1 divided by 0.05, 402 seconds. And we have 3 significant figures, so this is 3 significant figures. That's the same as 6.70 minutes, if you want to convert it to minutes. And notice the units, we have meters per second divided by meters per second squared. Notice that the meters cancel out. If what we have left here is actually second squared over second. One of these cancels out and you're left with seconds. So, okay. Flip over to page 36, and what we'll do is we're not going to solve these problems totally, but we'll just give you an idea of how to solve the rest of the problems. Page 36, question 8, 9, 10, refer to a graph on page 36, and it's of time versus velocity. And there's a 0 velocity here, and it looks, something like that. That's a bad drawing, but it looks something like that. Question 8, and now remember this is velocity, so velocity versus time, so a change in velocity, that is a slope, is a change in velocity over change in time, that's acceleration. So the slope is the acceleration. Over what interval, question number 8, over what time interval is the runner slowing down? Well, if this is a runner, he has a high velocity here. Remember, this is 0. He has a high velocity here, and then he's slowing down to a lower velocity. So he's slowing down here. Here he's gaining in speed. But here he's slowing down, until at this point he stops. So he's slowing down here. He's slowing down velocity here. But at this point, notice, because he's going in negative direction, he's actually picking up speed. He's just going in the opposite direction. So here he's not slowing down. Here he's actually increasing his speed. Okay, question number 9. What is a runner's acceleration at 6 seconds? And question number 10 is what is the runner's acceleration at 1 second? Well, you simply go to these individual times and you find what the slope of the curve is. So here the slope might be here, here the slope might be here. So the acceleration is the slope of the curve. Now one question that I've added, and I call it question number 11. It's not in the book, but at question number 11 is to find the total distance traveled. Find the total distance traveled from time equals 0 to time equal 20 seconds. And this starts out at 0 and it goes to 20 seconds out here. So now this is not in the book, this is not even one of the questions, but I've added it. How would you find the total distance traveled? by just knowing what the velocity is. This is actually a little bit of a trick question, although you have to think about it. And what I'm forcing you to do a little bit is to break this up into increments. If we break it up into second increments, imagine these are seconds. Okay. Notice from here, from 0 to 1, this is in seconds, from 0 to 1 second, what is the velocity? The velocity starts off here, it ends up here. So to know what the distance is, remember, the distance, remember velocity is equal to distance over time. So distance is velocity times the time interval. If we mark every average, if we go between every second, every half second, and we just estimate what the average velocity is in that half a second, okay? So we measure what the average velocity is in